Hello everybody, I would like to present you a thesis named Adaptive ADALINE Robust Training Algorithm under the Maximum Correntropy Criterion with Variable Center, authored by Oleg, Rudenko, Oleksandr, Bezsonov and Andrzej Szajna. The problem of ADALINE training in the presence of non-Gaussian interference is considered. The learning algorithm is a gradient procedure for maximizing the functional. In contrast to the commonly used Gaussian kernels, the centers of which are at zero and effective for distributions with zero mean, the paper considers a modification of the criterion suitable for distributions with non-zero mean. The modification is to use Correntropy with a variable center. The use of Gaussian kernels with a variable center will allow us to estimate unknown parameters under Gaussian and non-Gaussian noises with zero and non-zero mean distributions. The properties of its convergence in the stationary and non-stationary cases in conditions of Gaussian and non-Gaussian noises are investigated. At the beginning we will consider the problem of ADALINE training. ADALINE is described by the equation 1 where y observed outputs is observed output signal, x is a vector of the input signals of n by 1 dimension, and c is the vector of the required parameters also with the dimension n by 1. C is noise and n is discrete time. Now we are going to look at Correntropy as a measure of similarity. Correntropy, defined as a localized measure of similarity, has proven to be very efficient for obtaining robust estimates due to its little sensitivity to outliers. Its name emphasizes the relationship with correlation and also indicates the fact that its average value over time or measurements is associated with entropy, more precisely with the augment of the logarithm in the quadratic Rényi entropy, estimated with the help of Parsons windows. So for two random variables x and y, the Correntropy is defined as it's described by equation 2, where m is the expectation symbol, k in rotation invariant Mercer kernels, and sigma is kernel weights. Take in tasks of identification, filtering, etc. as functional, the Correntropy between the required output signal D and the model output signal or real signal Y is used. When using Gaussian kernels, the optimized functional then takes the form described by equation 3. Now we will talk a little bit about Correntropy maximization algorithms. The gradient optimization algorithm described by formula 3 with n equal to 1 will have the form described by equation 4, where gamma is the parameter affecting the rate of convergence. A significant drawback of this algorithm is the low convergence rate, which significantly limits the possibility of its use in identifying non-stationary objects. One of the approaches to solving this problem is to use the Correntropy with a variable center, as it is described by equation 5. Minimizing functional 5 with respect to the parameters of the model, we obtain an algorithm described by equations 6 to 8. And now we will take a look on multidimensional object. In case of multidimensional object, so if the object under study has several outputs, we have a situation when the output signal will be a vector signal and the row will be also a vector value, and the learning algorithm will have the form as it's described by formulas 9 and 10. Now we will investigate the issue of convergence of this algorithm. So we at the beginning consider the estimation error and described it as it's presented by formula 11, and then we will consider a steady state, and in a steady state we have a situation described by equation 13. To calculate the steady state value of the estimation error, we define mean of functional and mean of this functional as well. Consider the case of Gaussian noise. So using price theorem we obtain equation 14, and similarly by defining a mean of squared functional we obtain equation 15. After substitution of 14 and 15 into 13, we will receive the expression for the steady state error, limit of mean of squared error, and we will obtain formula 16 and 17. In the case of non-stationary case, firstly we assume that the estimated parameters are non-stationary, and we have a situation presented by formula 18. Then, taking into account formula 12, the estimation algorithm can be written as it's described by formula 19, and taking into account the statistical properties of signals and noise, we have mean of normalized squared parameters presented by formula 20. So in the case of non-Gaussian noise we have following situation described by formulas 21 and 22. Substituting 21 and 22 into formula 20, and after some simple transformation we obtain following equation for function s described by formula 23. This expression shows that s is a monotonically non-increasing function of the parameter gamma. From the condition of partial derivative of function s equal to 0, an equation can be obtained to determine the optimal value of the parameter gamma that provides the minimum value of function s. And we have following equation. And now we will consider some numerical experiments. The problem of ADALINE parameters adjustment was considered. Sequences of normally distributed quantities were chosen as the input signal x. When testing the robustness of the algorithm, an independent noise distributed according to the relay law with sigma equal to 1, and it was added to the output signal of the object. The histogram of such noise is shown at figure 1, and the simulation results for various values of the parameters are shown at figure 2. Figure 2 shows the graph of changes in the error when choosing the algorithm described by formulas 15 and 16 and algorithm 31 respectively, and following criteria is considered to measure changing of the difference between real output and real and expected outputs. So at this slide we have mentioned figures, figure 1 with noise distribution and figure 2 with different algorithms results. And now let's conclude. So they were considered an adaptive robust learning algorithm for ADALINE when using the information criterion of Correntropy with variable center as a learning criterion. The properties of its convergence in the stationary and non-stationary cases in conditions of non-Gaussian noises are investigated. The importance of choosing the weights of the Gaussian kernel, which affects the rate of convergence of estimation algorithm and the error in the steady state, is noted, and the expediency of developing procedure for adaptive correction of the kernel weights is indicated. The estimates obtained are quite general and depend both on the degree of non-stationary of the object and on the statistical characteristics of useful signals and interferences. Thank you for your attention.